These are the answers to the Chapter 9 and 10 practice quiz. Starting with multiple choice questions. Number 1. In this diagram, we have two atoms, and we are looking at the distance between the atoms, and we're looking at the potential energy. If this diagram looks familiar, which it should, take a look on page 346 in your textbook, and this is figure 9.14. It's talking about the distance between two hydrogen atoms, and you can see they're pointing to the energy minimum on the graph, represented by 0.74 angstroms. And at that point, there is a balance between the attractive and repulsive forces. So the correct answer to number 1 is A. The attractive and repulsive forces are balanced, so the two atoms will maintain an average internuclear distance x. X represents the bond length. In number 2, we have to decide the shape as well as the polarity for carbon dioxide, which you should know is a linear molecule, and sulfur dioxide, which, because of its extra lone pair on the central atom, is a bent molecule. So the correct answer is either A or D based on the molecular geometry. You should know that the dipoles are going to cancel out in carbon dioxide, making it nonpolar, whereas the dipoles are not going to cancel out in the bent sulfur dioxide molecule, so that is polar. Correct answer to number 2 is D. In number 3, let's consider what boron trifluoride looks like. It is a trigonal planar molecule, so we know that that represents the shape. We know that fluorine is more electronegative than boron, so it does contain polar bonds, but because of its symmetry, the dipoles cancel out, so it is a nonpolar substance that contains polar bonds. Number 3 is B. In number 4, let me call your attention to some information from your textbook about bond angles. So when there are lone pairs or non-bonding pairs of electrons on the central atom, they are going to exert greater repulsive forces on the adjacent electron domains. That means that the lone pairs will sort of squeeze the atoms together, making the bond angle smaller than the 109.5 you might expect if you had 4 atoms, like methane. So methane should be 109.5, but water should be less than that, around 105. Number 4 is B. In number 5, we have to consider bond angles again. So we have the NF3 nitrogen trifluoride molecule, which is trigonal pyramidal. We have our tetrahedral carbon tetrafluoride molecule, and we have our trigonal planar boron trifluoride. So as you know, carbon tetrafluoride has a bond angle of 109.5 based on the tetrahedral geometry. Boron trifluoride would be 120 for its bond angle because of the trigonal planar geometry. And even though you might expect nitrogen trifluoride to be around 109.5, remember that lone pair will compress the bond angle slightly, so it's going to be less than 109.5 for that reason, because of the lone pair on the nitrogen. So then in order from smallest bond angle to largest, we have choice A getting those numbers correct. In number 6, we're talking about hybridization. So hybridization is either sp, sp2, or sp3 in general. For this molecule, there are only 2 electron domains on either side of the carbon atom, so that would be sp hybridization. For the C2H2Cl2 molecule, there are 3 electron domains around each carbon, so the hybridization for that molecule is sp2. So correct answer for number 6 is B. Number 7, also talks about hybridization. The acetone molecule has two CH3 groups attached to a carbon which is bonded to an oxygen. And if you fill in the electron pairs, it ends up looking like this. So each of the carbons on the end has 4 electron domains, so they are sp3 hybridized, but that central carbon atom carries a double bond oxygen, but there are only 3 electron domains around that carbon. So that central carbon is sp2 hybridized, making the correct answer to number 7, D. In number 8, we're going to talk about sigma and pi bonds. Remember that the first bond you would draw, a single bond, is a sigma bond. If there is a double bond, that's 1 sigma and 1 pi. And when there happens to be a triple bond, that's 1 sigma and 2 pi bonds. Let's write the Lewis dot structures for these 4 molecules. So there is HCN. The next example has a hydrogen bonded to a carbon, and then the CO2H is that familiar carboxylic acid group which you've seen before with molecules like vinegar. And then we have C2H2, so a triple bond between the carbons, and C2H4, a double bond between the carbons. Again, if we count all of the first dashes as sigma bonds, and any multiple bond becomes 1 pi or possibly 2 pi bonds if there's a triple, let's go ahead and tally up the sigma and the pi bonds for each of these 4 molecules. Our first example would be 2 sigma bonds and 2 pi bonds. HCO2H, which is called methanoic acid, 4 sigma and 1 pi. Our next example is acetylene, 3 sigma bonds and 2 pi bonds. And then finally ethylene or ethene, 5 sigma bonds and 1 pi bond. So the correct answer for number 8 is C because of the dot structure and the bonds. Alright, moving on to number 9. We're now switching from chapter 9 to chapter 10. So this is a gases question. We have equal masses of neon and helium. The molar mass of neon is around 20 grams per mole. And the molar mass of helium is around 4 grams per mole. These two gases are both at the same temperature, so they have the same average kinetic energy, but the lighter gas, helium, is traveling at a faster average speed. So therefore, since helium is faster than neon, the correct answer cannot be C or D. Now, there are equal masses of neon and helium. However, there are not equal moles. And so because there are not equal moles, then there's not going to be the same pressure for each of these gases. So the correct answer we know is A. If you had, for example, 20 grams of neon, that would be approximately 1 mole. But if you had 20 grams of helium, that would be about 5 moles. And since there would be fewer moles of neon, the partial pressure of neon would be less than that of helium. Alright, number 10 is actually more about stoichiometry and writing a balanced equation than really about gases per se. Let's go ahead and write 4 balanced equations for the metal reacting with excess hydrochloric acid to produce hydrogen gas. We're going to write a single replacement reaction for the metal and hydrochloric acid. We're going to produce a metal chloride and hydrogen gas. To balance this equation, I'll put a 1/2 in front of the hydrogen. That way I can keep 1 mole of sodium in my balanced equation. Next one's going to make magnesium chloride. And to balance that equation, I would need to put a 2 in front of the HCl. For aluminum chloride, that would be AlCl3. I would need to put a 3 in front of the HCl, and then to get 3 hydrogens on the right, I'm going to use a fractional coefficient just to keep 1 mole of aluminum present in all of these equations, we have 1 mole. Calcium's in the same family as magnesium, so it would balance in the same way. So as you look at these 4 balanced equations, the one that would produce the largest number of moles of hydrogen gas, starting with 1 mole of the element, would be aluminum. All right, moving on to number 11. Carbon monoxide has a molar mass of 28 grams. Hydrogen gas, the diatomic gas, has a molar mass of 2 grams per mole. Now, if we have 14 grams of carbon monoxide, we have half a mole. And if we have 7 grams of hydrogen gas, we have 3.5 moles. Remember that mole fraction would be moles of one gas divided by total moles. In this case, the total number of moles is 4. So the mole fraction of carbon monoxide is 0.5 divided by 4, which is the same as 1 over 8. And the mole fraction of hydrogen would work out to be 7 over 8. If we multiply these mole fractions by the total pressure, 2.4 atmospheres, then we end up with a partial pressure of 0.3 atmospheres for the carbon monoxide, and then 7 times as much for the pressure of hydrogen. So that 1 to 7 ratio in terms of moles would be consistent with 0.3 and 2.1. There are 7 times as much moles of hydrogen, so the pressure of hydrogen should be exactly 7 times as much as the pressure of carbon monoxide. Number 12 is talking about deviating from ideal behavior. So take a look on page 409 and 410 in your textbook. With respect to pressure, real gases do not behave ideally at high pressures, normally higher than 10 atmospheres. And then as far as temperature is concerned, in general, the deviation from ideal behavior increases at low temperatures. So we're looking for low temperatures and high pressures. Correct answer to number 12 is B. Number 13, we have a graph showing the distribution of various speeds for a sample of oxygen gas at 25 degrees Celsius. Now here's a graph on page 403 that shows the distribution of speeds, and we're comparing 0 degrees Celsius with 100 degrees Celsius. So what do we learn from this graph? As the temperature of a gas increases, the average speed of the particles increases, and the distribution of speeds broadens out a bit wider. Does this kind of graph help us answer number 13? Well, not exactly, because we're not changing the temperature, we're changing the identity of the gas. Let's compare oxygen with hydrogen. Now on page 406 you can see that we are looking at different gases, and we discover that as the molar mass of a gas decreases, the average speed increases, and it does spread out a bit wider. So look at the hydrogen graph and compare that with the oxygen graph. So the best choice for number 13 is A. All right, moving on to number 14, we have 3 different gases, argon, neon, and helium, and we are comparing what's going to happen when we mix them all together. So let's start with argon. The pressure is 2 atmospheres. Now the pressure of neon would have to be half as much based on the particle diagram, and it says that the ratio of the numbers of the atoms in these 3 vessels is 2 to 1 to 6. If we combine all 3 gases into a 1 liter container, then the total pressure should be 9 atmospheres. But we're not combining them together in a 1 liter container. We're combining them together in a 2 liter container. So is the pressure going to be 9 atmospheres? No. In fact, when you double the volume, you cut the pressure in half. So the correct answer to this question is the pressure will be 4.5 atmospheres. All right, number 15, we're comparing argon and helium. Both gases are at the same temperature, so they have the same average kinetic energy. So if they have the same average kinetic energy, that means that the answer cannot be A. When we compare their volume and temperature, they are the same, identical containers, so same volume and temperature. So what's different? Well, pressure is different, so that means that the moles must be different. If there is twice as much pressure in the helium container, then there should be twice as many moles of helium. So the correct answer is that the number of gas particles in container B is greater than that of container A. As far as the other choices B and D, you know that helium is lighter and faster, so therefore the average speed of container B would actually be greater, so I can eliminate choice D. And what would 2 moles of helium weigh on the periodic table? Well, that would be around 8 grams. 2 moles of helium weighs around 8 grams. And a mole of argon weighs about 40 grams. So even though we have twice as many moles of helium, the density of the gas in container B would actually be less than the density in container A because helium is so much lighter than argon. All right, moving on to number 16. We have xenon, which has an initial pressure of 1.7 atmospheres. All of the xenon reacted, forming a solid compound, so the final pressure of xenon is 0 because it all reacted. Initial pressure of fluorine gas is 8 atmospheres, and at the end, after the reaction, the final pressure of fluorine is 4.6 atmospheres, so some of the fluorine reacted. What's the change in the pressure of xenon? It's 1.7. What's the change in pressure for fluorine? Well, 8 minus 4.6 is 3.4. Now look at that. The change in pressure for xenon is exactly half as much as the change in pressure for fluorine. So the amount of fluorine that reacted is twice as much as the amount of xenon that reacted. These pressure ratios are proportional to the mole ratios. So what have we learned here? That in terms of this chemical reaction, every time 1 mole of xenon reacted, 2 moles of fluorine reacted with it. So our balanced chemical equation looks like this, and that forces the fluorine compound to be not XeF2 as you might have thought, but rather XeF4. So correct answer for number 16 is D. Okay, on to the free response questions. In number 1, we're going to fill in the missing information about molecular geometry and polarity. So BeF2, beryllium difluoride, looks like this. It's a linear molecule, and it is non-polar because the dipoles cancel out. The oxygen difluoride is going to look like this, and it's a bent molecule, but therefore because of its bent shape the dipoles do not cancel out. It is a polar molecule. Xenon difluoride looks like this. It is linear, of course, and therefore non-polar. Carbon tetrafluoride has a tetrahedral geometry, and because all the dipoles are going to cancel each other out, the symmetry makes it non-polar. Now sulfur tetrafluoride has an extra lone pair, so the geometry becomes seesaw, and that is not going to help in terms of symmetry. All the dipoles will not cancel each other out, so that's a polar molecule. And then finally, xenon tetrafluoride is going to have square planar geometry, and symmetry will make this molecule non-polar as all the dipoles cancel out. Alright, that was part A. Part B, the beryllium difluoride molecule is linear, so therefore the bond angle is 180. The carbon tetrafluoride molecule is tetrahedral, and the bond angle is 109.5. Beryllium difluoride has exactly 2 electron domains on the central atom, so its hybridization is sp. Now oxygen difluoride, well, think about this. This is on page 349. Here's a water molecule. Water is bent, just like oxygen difluoride is bent, but there are 4 electron domains, 2 bonding domains and 2 non-bonding domains. A total of 4 electron domains makes it sp3 hybridized. Carbon tetrafluoride also sp3 hybridized, 4 bonding domains. All right, part D, we have to make a prediction about the bond angle in oxygen difluoride. In other words, are those lone pairs or non-bonding pairs on the oxygen atom going to affect the bond angle? And you know the answer is yes. They're going to compress the bond angle. We saw this earlier on page 338. Non-bonding electron pairs exert greater repulsive forces on adjacent electron domains and tend to compress the bond angle. So the bond angle should be less than 109.5 because the oxygen atom has 2 non-bonding pairs of electrons which are going to exert greater repulsive forces, and this tends to compress the bond angle so it's less than 109.5. In number 2, we are starting with a compound called ethanol, C2H5OH, and as that compound is being heated in the presence of a solid catalyst, we're producing 2 gases, ethene, C2H4, and water vapor. The student starts with 0.200 grams of ethanol, and after it was heated, some of that reaction did occur. Maybe not 100% yield, but we definitely got some product. Now the volume of collected gas was 85.4 milliliters, and 625.0 torr was the atmospheric pressure. So what are we going to do with the 625.0 torr and the vapor pressure of water? So I think you remember this from the lab. To get the pressure of the dry ethene gas, we have to subtract the vapor pressure of water from the atmospheric pressure. And so we get a pressure of ethene gas. Now it says calculate the number of moles of C2H4 that are actually produced. Well, how are we going to get moles? All we have is pressure right now. Let's take a look at the ideal gas law. We'll solve for N. So N equals PV over RT. So P, the pressure, is 589.3 torr. The volume they gave us in the problem, they gave us the temperature in Celsius. We convert that to Kelvin and we get 305 Kelvin. And then we're using the gas constant, which has units of torr. So we plug all that into the equation, solve for a number of moles, and we get 0.00265 moles of ethene actually produced. How many moles of ethane would be produced if the reaction went to completion? Well, that's based on how many grams we started with. We began with 0.200 grams of ethanol. Let's convert that from grams to moles. And remember, in the balanced chemical equation, it was a 1-to-1 ratio between moles of ethene and moles of ethanol. So if we do this math, we get 0.00434 moles. That's how many moles of ethene would have been produced if the reaction went to completion. So the percent yield would be equal to the actual yield divided by the theoretical yield. So in this case, 0.00265 moles that was actually produced divided by 0.00434 moles that would have been produced if the reaction had gone to completion. So we get 61.1% yield. In part C, we're given the diagrams. We have to fill in the electron pairs. For ethanol, that's going to be all single bonds, and don't forget the lone pairs on the oxygen. And for ethene, when you do the bonds, you're going to run out of electrons unless you make a double bond between the carbons. So those two diagrams now have the complete Lewis electron dot diagrams filled in. All the lone pairs, bonding and non-bonding, are there. All right, In part D, let's talk about the hybridization. So for ethanol, each carbon has 4 electron domains, so sp3 hybridization. In ethene, each carbon has 3 electron domains, so sp2 hybridization. The bond angle for ethanol is based on tetrahedral geometry, so 4 electron domains, 109.5, and the bond angle for ethene is based on trigonal planar geometry for the sp2 hybridization, so 120. All right, number 3. We have a sample of propane, and we're going to react that with oxygen and produce carbon dioxide and water. The balanced chemical equation for this combustion requires coefficients of 3 next to the carbon dioxide, 4 next to the water, and then with a total of 10 oxygen atoms on the right, a 5 next to the O2. In part B, we have gone from 0.2 atmospheres of propane down to 0 because all of it reacted. We've gone from 1.4 atmospheres of oxygen down to 0.4 atmospheres. So not all of the oxygen reacted. But remember, we had that question on the multiple choice with xenon and fluorine. It's a similar thing going on here. The change in pressure for propane is 0.2 atmospheres, and the change in pressure for oxygen is 1 atmosphere. Now look at that change in pressure for oxygen. It's 5 times as much as the change in pressure for propane. Well, that makes sense because of the coefficients in our balanced chemical equation. Then the change in carbon dioxide would need to be 3 times as much as the change in propane. So 0.2 times 3 is 0.6. The change in water would be 4 times as much relative to that of propane. So 0.2 times 4, 0.8. So now that we know these numbers, let's calculate mole fraction. We have to calculate the mole fraction of oxygen in this vessel before and after the reaction. You might think, how can we do this? Should we convert from the ideal gas law into moles of oxygen? Well, there's an easier way to do this that does not involve the ideal gas law. Remember back in your chapter 10 packet, we said that you can calculate the mole fraction by simply doing the pressure of one gas divided by the total pressure. Well, we can do that here. So before the reaction occurs, we have a pressure of oxygen of 1.4 atmospheres, and the total pressure before the reaction is 1.6 atmospheres. That gives us a mole fraction of 0.875. Now, after the reaction has occurred, we have a pressure of oxygen, which is equal to 0.4 atmospheres. And if we add up all those gases, the total pressure is 1.8 atmospheres. So that ratio gives us a mole fraction of 0.222. All right, moving on to part D, the last question. Calculate the mass of propane that is consumed. Remember, there was 0.2 atmospheres of propane, and then all of it was consumed. So the pressure of propane was 0.2 atmospheres. It was a 5-liter reaction vessel, and the temperature in kelvins is 400. Notice I'm using the gas constant that has atmospheres with it. So this will give us moles of propane. I'm going to go ahead and extend my precision to a few extra decimal places before I round off. Let's convert moles of propane, so 0.0304655, into grams of propane using the molar mass. And so we do this math and we get 1.34 grams of propane that was consumed. All right, well, that wraps up the answers and explanations for the Chapter 9 and 10 practice quiz. I hope that was helpful. Thanks for watching.